All right. Good afternoon, everyone. I'm not in camera. So we're moving on to the next unit. So the first unit was more cosmology and the universe at large, and this next unit is focusing on the solar system. And what's in our solar system. How it formed, what's there. This unit it shouldn't take too long to get through. Okay. So we've already learned about stars and how stars form and the protostar. Right? And as that protostar is spinning, there is that disk of matter spinning around it. And as the protostar shrinks, right, it speeds up, the spinning speeds up, and that disk expands, right? And we call this like the protostar disk or the protostellar disk. The material in that protostellar disk is what ends up forming the planets in a solar system. And my classroom door is open. I'm just going to pause it here and go close that. Okay. So we've got 8 properties of our solar system. The first property is that each planet is relatively isolated in its own space, and it has its own orbit. The orbits are nearly circular. Now, they tend not to be perfect circles. They tend to be elliptical, like an oval, but they're mostly circular. Sorry, I got a word there's in my mouth. And the orbits of all the planets, right? Protostar formed. We had the disk. Let's get in the center of the camera. We had that disk, and from that disk, the planets formed. So all the planets formed from the same disk. Because they all formed from the same disk, they all lie in the same plane. I'm just chewing up this word. And the planets should all orbit in the same direction as the sun is spinning. Because as the protostar collapsed, it started to spin. And all of that interstellar cloud started to spin all together, and that spin continued. And in that direction of turning, the planets kept the planets that formed out of that spin, they're in the same direction as the star. One second here. Okay, again, sorry about that. And I just kind of get this centered, right? So, okay, well, a little better, I think. So the interstellar cloud collapses. As it collapses, it starts to rotate. Okay, as it rotates, just like a pizza maker, spinning pizza dough, you get parts of that cloud start to spread out, creating the protostellar disk. Okay, so the center part, which becomes the protostar, is spinning in this direction. The protostellar disk is spinning in the same direction as the protostar. That protostellar disk became the planets. Okay? So they're moving or orbiting in the same direction as the protostar, which is now the actual star, is spinning. Number 5, our planetary system is highly differentiated. So what we mean by that is that there is a lot of differentiation, or the planets are different from each other. And at a basic level, we can look at the inner planets. So Mercury, Venus, Earth, and Mars, right? Those 4 planets, they're all rocky, or they're terrestrial. Right? And then you can look at the outer planets, right? So Jupiter, Saturn, Uranus, Neptune, they are the gas giants or the gas planets, where there probably is a solid core in the center, but around it are cold gases. Okay, number 6, asteroids are very old and exhibit a range of properties not characteristic of either the inner or outer planets or their moons. Okay, so we've got these ancient rocks, okay? And these ancient rocks, right, they actually may have been the things that became planets and moons as they combined into each other. Okay, outside past Neptune for number 7, we've got a belt of really cold, icy objects that's known as the Kuiper Belt. And I'll put a diagram up on today's post with what we think the solar system looks like. And beyond the Kuiper Belt, right, and it's not within the disk, right? It's just not on the same plane of orbit. That same plane of orbit we call the ecliptic. So the planets are all on that disk, the ecliptic, right? The Kuiper Belt is on the ecliptic, but past that, around our sun in a dome, not in a dome, in a sphere, 360 degrees, are these objects very far away, very, very cold, right? That become our comets, right? So the Oort cloud, right, and is made up of comets, and these are like really primitive icy fragments, and they don't orbit in the plane of the ecliptic. So outside the planets, we've got the Kuiper Belt, where we've got asteroid-sized icy bodies, and then we've got the Oort cloud, where we've got icy bodies, but they're not on the interstellar disk; they're orbiting around. Let's move me over here. And shrink this a little bit if I can. I can't. So I'll just chill out here in the corner. So how our solar system was formed, and it shares the beginning of star formation. Right? We've got a large cloud of interstellar gas and dust a light year across, and it starts to collapse. It could have been triggered by shock waves from a supernova, right? Some other gravity, it's the gravitational forces of a passing interstellar cloud. Two interstellar clouds could have bumped into each other, but something disturbs it, and due to gravity, it begins to collapse. Right? And as it collapses, it becomes hotter and hotter, denser and denser, and eventually it becomes so hot that the material at the center starts to glow. Right? It's not. It's kind of like when you heat iron up and it gets red hot. Right at the center of this interstellar gas cloud, right? The matter become, and these interstellar gas clouds are mostly hydrogen and dust. It becomes super super hot and it becomes luminous. Right, it starts giving off light. Right? Eventually, as we know, that protostar will, if it becomes hot enough, right, if it reaches that 15 million degrees Kelvin, you then have nuclear fusion and you now have a main sequence star. Okay. So this is what it's showing here. We have the gas cloud collapsing, right? It starts to spin as it spins, or sorry, as it starts to collapse, it gets smaller, the spin increases in speed, right? It forms the protostellar disk, okay? The protostar gets hotter and hotter, more and more luminous, and eventually it can become a main sequence star. So this process of spinning and spinning faster and faster as you collapse is the law of conservation of angular momentum. So a decrease in size of a rotating mass must be balanced by an increase in its rotational speed. Okay? So we have to conserve momentum. It's kind of like a principal law of physics. Right? So that if you have a very large object that's spinning slowly, but if that large object becomes smaller, that energy that was spinning the massive object is now spinning a smaller object, so it starts increasing in speed. So a decrease in the size of a rotating mass must be balanced by an increase in its rotational speed, causing the nebula's shape to change. So instead of being a big puffy cloud, you end up with the protostar in the center and a disk. Centrifugal forces due to rotation. So if you, as things spin, it puts a force externally. So centrifugal forces due to rotation oppose the contraction perpendicular to the axis of spin. Right. So the forces oppose the contraction. Right. So contractions pulling inwards. Right. Centrifugal forces along the axis of spin, right, or sorry, perpendicular to the axis of spin. So if we're spinning this way, right, we've got forces pushing out. I can't see myself because I moved the. Let me move it back in the center. So if we're spinning this way, centrifugal forces are pushing outwards. So the cloud is collapsing, sorry, but we've got centrifugal forces pushing outwards. Everywhere else it's collapsing, top and bottom, except perpendicular to the axis of spin. So the nebula collapses, right, along the axis of spin, so up and down, but doesn't collapse perpendicular, creating the disk. So the end result is a nebula flattening into a swirling mass known as a solar nebula. Okay, so remember, the nebula is collapsing, but it's spinning. As it spins faster and faster, centrifugal forces oppose the contraction perpendicular to the spin, so it doesn't want to collapse horizontally, but it continues to collapse vertically, right? Leading to this flattening of the disk with the protostar in the center, leaving the solar nebula. So I'm just going to have a sip of my drink. Give me a moment here. Fizzy. Okay, where was I? Okay, so from this flattened disk, we end up forming our planets, right? So the planets form, we have our solar nebula, and the planets form in the solar nebula here. We can see a progression from a cloud into a solar system. And the fact that the planets formed from the flattened disk explains 1, 2, 3, and 4. Okay, each planet is isolated in space. The orbits of planets are nearly circular, so the same shape as the disk. The planets all lie in the same plane, and they orbit in the same direction as the spin of the sun because they came from the same cloud. The theory that planets formed from this disk is called the nebular theory. In the nebular theory, it was thought that the disk was hot. This is not possible, though, as the heat would not allow matter to accumulate. So if the disk stayed hot, right, matter doesn't want to, gather. If matter's cold, it likes to clump together. If it's hot, matter will like to fly apart. If you remember the particle theory of motion, if you heat up a solid, a liquid, a gas, the particles move more and more and more, right? And as they move more and more and more, they will push away from each other. So the idea of this nebula staying hot all throughout is unlikely because it would as the particles had more energy and more motion, they wouldn't want to collect and slowly form planets. Right? So the nebular theory wasn't quite right. So we then expanded to what we call the condensation theory. So the idea behind the condensation theory is is that there's these interstellar grains of dust, right? Leftover remnants from supernovas, right? When stars exploded, right, in a supernova, or when stars gave off a planetary nebula if you were a smaller star. Right? So interstellar space, the space between stars, is full of these microscopic dust grains. Okay? And the theory is that these dust grains, right, they can absorb heat from the nebular cloud, right? So they can absorb heat from the solar nebula here. So they can absorb heat and then they give it off as infrared radiation. So these solid chunks of matter, even though they're tiny, right, these tiny grains of matter, they slowly bleed away the heat energy of the nebular cloud, right? And they of the solar nebula, sorry, and they start making it a little cooler. They allow it to cool over time. So the excuse me, the dust grains cool the warm matter by radiating its heat away in the form of infrared radiation. And by bleeding away that energy, the cloud gets cooler and cooler. And because it gets cooler and cooler, right, it can collapse more easily due to gravity, right? So as the cloud cools, it collapses more easily under the force of gravity as the molecular motion slows. So the particles, and they're hot, they're moving around really fast, zipping around. As they get cooler, they start moving more slowly. And because they're moving more slowly, right, gravity can start to catch them and pull on them. And it slowly starts to pull, I'm drifting away from the camera, it slowly starts to pull them together, right? So matter can start to accumulate around each other, right? And we start to build up matter in small spots. So these dust grains act as a condensation nuclei, so matter can condense around it. So microscopic platforms to which other atoms can attach to. This forms larger and larger clumps of matter, right? And these larger clumps, right, they can start to form the asteroids. And if they keep on building up other matter or if they pull in other clumps, they can eventually become extremely large and become a planet. So the clumps stick to other clumps in a process called accretion. Eventually, this should say they, not the, eventually they form planetesimals, objects large enough, right? So they could be like a few hundred kilometers across, right? So we're starting to form small planets, right? These small planets, these small planetesimals, right, can keep accreting matter and become bigger and bigger. Or these small planetesimals can pull other planetesimals in, and they can start to form larger and larger celestial bodies, right, forming the bigger and bigger planets. So these the more matter you have in a spot, the bigger the condensation nuclei and the matter it's accreted, the stronger its gravity. So if I had a small rock, right? So let's say this geode here, I got this small rock. Okay, it would have more gravity than this small styrofoam ball because it's more massive. Right? It has stronger gravity. Both of them have gravity, and they're both pulling objects towards them. Right? There's all matter has gravity. The more mass you have, the stronger the force of gravity. So as these planetesimals got bigger and bigger and bigger, their gravity grew stronger and stronger. They started to pull more matter in. So large objects have more gravity and they sweep up almost all of the original material in the solar nebula and they start to form a few large protoplanets. And over time, those larger protoplanets start pulling everything else into it. Right? So as the number of planetesimals decreases, right, so here we start with a bunch of planetesimals, and then as time progresses, we get some larger planetesimals, and they've started absorbing some of the smaller ones. So we start getting spaces in the orbits as some of those smaller planetesimals have been absorbed by the larger ones. And then the bigger you are, the stronger your gravity, and this process keeps happening till eventually you end up with these planets with very distinct separate orbits, as I mentioned on the first slide. So you started with a cloud, right, of planetesimals all orbiting the star, right? Then gravity started pulling them together. Some of them got bigger than others for a variety of reasons. The bigger ones had more gravity and they started pulling the smaller ones in. And eventually, you end up with all these big planets that have cleared their orbits of a lot of the smaller junk, right? So a lot of the planetesimals are gone, and you now have these distinct planets with distinct orbits. So gravity caused collisions, right? I could have a large planetesimal, right, and I could have a smaller planetesimal pulled into it, okay, by gravity, right? But these two solid pieces of matter collided, and as they collide, we get fragmentation, right? They break up, they break, and now we have all these fragments floating around, right? And these fragments mostly got swept up into, they could get pulled back down into the bigger protoplanet, or they could be flung out into the solar system where they get gobbled up by other protoplanets. So that early solar system was a pretty busy place, right? Lots of planetesimals floating around, lots of gravity pulling planetesimals into each other, smacking into each other, breaking up, sending pieces everywhere, right? And then those pieces could be pulled back in or absorbed by other protoplanets. But eventually, as time passed over billions of years, the number of these free floating fragments decreases, and all those objects get pulled into other planets. So early on in Earth's history, long before we were here, right, or even if you look at the moon, you can see the moon is covered in craters, right? But now, in our current time, there's not a lot of strikes on the moon. We don't see new craters forming on the moon very often, if at all, right? You look at the moon, you see all those craters. That is evidence of the history of our solar system when it was full of all these tiny planetesimals, right, and all these fragments floating around and all these collisions happening. But over time, these collisions become less and less frequent because all that free floating fragments get pulled into the larger bodies. Okay. And it's kind of slowly clearing out our solar system of all the fragments. There's still lots of fragments around, though. There's still asteroids and meteors around, but not nearly as much as it used to be, right? You know, it would be like, a billion years ago, sorry, traveling through our solar system would be like walking across a battlefield and all these bullets whizzing past you. Right? But now there's much fewer particles floating around. Sorry, I just got an email. Just got to check that. I'm going to hit pause here. Okay. This next slide here is referring to the differentiation of our solar system. Why the inner planets are rocky. Okay. So why the inner planets are rocky and why the outer planets tend to be made up of gas. And that's all due to temperature. So I want you to imagine the protostellar disk, right? We've got the protostar in the center. It's very hot. Okay, it's very hot there. And as it becomes a main sequence star, it gets hotter and hotter. The further away you are from the protostar, the cooler it gets. So temperature resulted in the differences we see between our rocky planets and our gas planets. Okay, so let's read along here. And I'll just chill here for now. So the differentiation of the solar system. So temperature played a key role in the differentiation of the solar system, which led to our terrestrial or rocky planets versus our gas giants. Okay, so as the primitive solar system condensed and flattened, nope, and here for a little bit. So as the primitive solar system condensed and flattened as it was spinning, temperatures increased near the protostar or the protosun. The outer regions of that spinning disk were cooler. Higher temperatures near the center caused the aforementioned dust grains to be split apart into excited atoms. So near the protosun, it was super hot. And these dust grains, they would get vaporized into their basic elemental constituents, into their basic atoms. They would also get ionized, right? Electrons would get stripped away. The further away you were from the sun, the cooler it was, and fewer of these dust grains got atomized. Okay, so essentially what that means, when you were close to the protosun, a lot of the lighter dust grains, right? The lighter elements, not the elements, sorry, the lighter compounds, the lighter molecules, right? They would get vaporized, and only the heavier elements could survive. The further away you were, right, the colder it was, the lighter elements, the lighter molecules didn't get vaporized, so they could accumulate far away from the sun. So high temperatures near the center caused the dust grains we talked about, that were the nuclei for forming protoplanets, to be split apart into excited atoms, so they were destroyed. While further away, more dust particles could remain intact. So as the gases cooled, right, and they cooled more rapidly far away from the sun because there were more dust grains, right? So as the gases cooled more rapidly to where dust was present, so further away the dust was present, up close, fewer dust grains because they were being atomized, right? New dust grains began to condense or freeze out. At any given location, only materials able to survive the temperatures at those locations could freeze out. Okay? So close to the sun, right? Materials close to the sun, right? Sorry, planets close to the sun, all that could really freeze out were metals and rocky materials. So if we look at this graph here, we've got temperature in degrees Kelvin, and we've got distance from the sun in astronomical units. An astronomical unit is about 150 million kilometers, or the average distance from the Earth to the sun. So one astronomical unit is the average distance from the Earth to the sun. 2 astronomical units is twice that distance, right? 3 astronomical units, 3 times that distance, and so on. Okay, so we'd have Earth here at 1 astronomical unit at a temperature, or when it was forming, around 1200 degrees Kelvin. At those temperatures, metals could freeze out, right? And rocky materials could freeze out. Right? As we start getting further and further away from the sun, right, we start to freeze out. We can start freezing out water. We can start freezing out ammonia. We start freezing out other gases. So the inner regions, only metals and rocky materials could freeze out. Right? The energy there wasn't hot enough to break up metals and rock. Okay, so atoms of rock and metal were not destroyed by the heat. Right? Atoms of lighter gases like ammonia and methane, right? They would be destroyed by the heat. They would break up. But when you reach distances further out, right, it was cold enough for some of these materials to freeze out and become solid. So we start getting ice. We start getting frozen ammonia and frozen methane, right? These gases form our gas giants, as well as hydrogen and helium. You'll find like Jupiter's mostly hydrogen. Well, not a huge chunk of it's hydrogen. Close to the star, these lighter materials would be vaporized. Further away from the star, those lighter materials, it got cool enough, they froze out and solidified. Or if not solidified, they started to cool down and condense to the point where they could become like clouds. The inner planets, too hot, those materials couldn't exist at the inner planets, and all that could exist at the inner planets at that time, all that could freeze out was metals and rocky materials. So, this explains why the four inner planets are all rocky. And then the four outer planets are all made up of ammonia and methane and other lighter materials like hydrogen. Okay, so it's important to note here metals and rocky materials, right, that we find at the inner planets, those would freeze out where it was cold far out, far out in the solar system, right? So they would freeze out at great distances. But the inner system was too hot for the lighter materials. So that's why at the inner system, we only see the rocks and the metals. Okay. Rocks and metals would exist deep in the solar system, deep way out there, but we don't see the light materials in the inner solar system. It's too hot. So as matter starts to freeze out, right, and gravity starts pulling it all together, we form the core of the planets we see today. So next, we get the ideas that, okay, the inner planets, Mars, Mercury, Venus, and Earth, right? They're rocky and they're metallic, right? Because it was too hot for the lighter metals to freeze out there. That makes sense. But then we look at their size in comparison to Jupiter, Saturn, Uranus, and Neptune. Those planets, we call them the Jovian planets, right? Jove was another name for Jupiter, right? So the Jovian planets are extremely large. So these two theories here, the two competing theories of how the Jovian planets formed, kind of try help us to understand why the Jovian planets or the gas giants were so large. So the first theory, the core accretion theory, due to the abundance of freeze-outs, so lots and lots of material, lots and lots of methane and ammonia and lighter material, right, was able to freeze out, right? Not as much material could freeze out in close to the sun because it was too hot. But when you're further out, right, it's a lot cooler, so all types of material can freeze out. So due to the abundance of freeze outs and dust grains, right, distant from the sun, the protoplanets could grow quickly. So you had a lot of different matter freezing out, right? You had a lot of dust grains there as well. Remember, if you're close to the sun, the dust grains were vaporized. If you're further away from the sun, the dust grains remained intact. So you got lots of freeze outs, lots of original dust grains, which are helping to cool down the cloud. So, due to the abundance of freeze-outs and dust grains distant from the sun, the protoplanets could grow very quickly, right? So they could form very fast because it was cold, lots of gravity due to all these dust grains and freeze-outs, and they could grow quickly. The quicker they grew, the stronger their gravity. So the protoplanets grew quickly, developed very strong gravity, pulling in the remaining solar nebular gas, so the remaining hydrogen, right, that was part of the cloud, and the remaining helium that was part of the cloud, and they quickly formed the gas giants. Okay, so one more time, right, being far in the core accretion theory, being far away from the sun, okay, the dust particles weren't vaporized, right? You had lots of freezing out of the lighter elements and the heavier elements. So you had a huge amount of material, right? Dust grains that didn't get vaporized and freeze out. Right? So you had this huge amount of material, right? And these dust grains also helped cool things down around them very quickly. So the protoplanets grew massive. There was a lot of mass to work from. So they grew very quickly. And as it got bigger and bigger, more and more gravity, and all that gravity could pull in the remaining hydrogen gas and helium that was still left over from the solar nebula, creating a gas giant. The next theory is gravitational instability theory. So, if you remember from when we talked about protostars forming and how a large gas cloud could fragment and form smaller gas clouds, and then each one of these smaller gas clouds could form a star. This is kind of similar to that, but on a much smaller scale. So instabilities in the outer gas cloud, much like the ones that formed a protostar, cause parts of the cloud to collapse due to its own gravity. So you've got the major center collapse, making the protostar, but we might have, where Jupiter was, some gravitational instability that caused a minor collapse there. And we cause parts of the cloud to collapse under their own gravity, and they bypass the core accretion stage, and they soon become massive enough, right, that they become massive. They have their own gravity to start pulling in more gas and more dust grains. So instead of just having the collapse at the center, you've got a collapse where Jupiter was, and a collapse where Saturn, Neptune, and Uranus was. So those smaller collapses, essentially, according to this theory, are forming small protostars, but they were never big enough, right? They weren't big enough to have as much gravity, and they couldn't generate heat the way a protostar would, so they never became a luminous protostar. Okay? The moons of the Jovian planets, the gas giants, probably formed as a result of the condensation accretion within the gravity well of the gas giant, forming a mini solar system. So just like the solar nebula formed the planets, right? It's possible that in that solar nebula where we have the gravitational instability theory forming the gas giants, those gas giants developed their own protostellar disks, and those little protostellar disks of their own became the moons of those planets. So instead of just one protostellar disk in one massive cloud, right? We've got a massive cloud with the main protostellar disk and the protostar, and within it, we've got these separate pockets of gravity forming large gas planets with their own disks that became their own moons. You kind of have to think about that a little bit. If you're confused, message me. Okay, so the next topic is the asteroids and comets. And they exist in the Kuiper Belt, which I'll show you the slide a little later on, and in the Oort cloud. The Kuiper Belt is along the ecliptic, right, along the same plane, but it's out past Neptune. The Oort cloud is past the Kuiper Belt, and it's 360 degrees around the solar system. So, follow along, please. In the inner solar system, the planetesimals that escaped capture, right? So the small planetesimals that weren't gobbled up by larger planetesimals, right, were boosted out past Mars, where they formed an asteroid belt. So the idea is that the gravity kind of of the other larger objects slung some of the planetesimals out into an asteroid belt between Mars and Jupiter. And it's thought that, and again, this is just kind of speculation, that the gravity of Jupiter, right, was pulling on those planetesimals, and it never allowed them to coalesce to form a planet where the asteroid belt is. So between Mars and Jupiter, we've got these two competing forces of gravity that stopped the tiny planetesimals from coalescing into a larger planet between Mars and Jupiter. So the end result is you've got all these fragments traveling around in the asteroid belt, smashing into each other and fragmenting, but not coalescing, not grouping together and forming a big planet, because the gravity of Mars and Jupiter keeps pulling them apart. In the outer reaches, right, so we're talking deeper into the solar system, it's thought that the gas giants, right, their gravity could have taken planetesimals and flung them to the far reaches of the solar system. Okay, some of them possibly even out of the solar system. So the gravity wells of the Jovian planets flung planetesimals out of the solar system into orbits far from the sun. Some may orbit outside of Neptune in what is the Kuiper Belt. Okay, so when they say flung out of the solar system, they're saying flung past Jupiter. So some may have been flung outside past Jupiter. Sorry, let me rephrase that. So that they may have been flung out of the solar system past Neptune, right? Past the last planet. So we're saying that some of these objects orbit, when we know they are there, that orbit outside Neptune in the Kuiper Belt. Others may have been flung even further, being flung even further into the Oort cloud. Computer simulations have shown that Uranus and Neptune can slingshot planetesimals out into the Kuiper Belt. Okay? Others can be punted inwards towards Jupiter and Saturn, whose immense gravities, because they're much bigger, can then shoot them out into the Oort cloud. So here in this image, right, we've got the Sun, right, Jupiter, Saturn, Uranus, Neptune. We're not really showing the inner planets, right? So inner planetesimals can be ejected out to the Oort cloud, right? Outer planetesimals can be deflected inwards, right, and then out to the Oort cloud, or outer planetesimals can be ejected into the Kuiper Belt. Okay, so what we saw then is this clearing of the inner solar system, where there's less, where there's no planetesimals really floating around inside. The gravity of the planets, right, pump things out towards Saturn and Jupiter, and then they kick things way out into the Oort cloud, and then the outer planets also deflected the planetesimals out into the Kuiper Belt. So if we look at this image here, this image is showing our solar system, okay? Then the Kuiper Belt along the same plane. And then outside the Kuiper Belt, we have the Oort cloud. Okay, and that ends this discussion.